Yeah, so we'll take a short break from inflation because I'll talk about cold dark matter. I'm Luca, I'm a local postdoc here working with K-Freeze, but I'll talk about some work I've done with my PhD advisor, Paolo Dondolo, and by myself recently on Axions and ALPs as the cold dark matter. So, all right, just a brief review of the Axion as has not been given in this workshop yet. Well, the QCD sector of the standard model allows for a term that violates CP. Oh, sorry. It violates CP. How do I point? Okay. For a term that violates CP, but it's not observed experimentally. This has been solved by postulating a new U1 symmetry by Pecei and Quinn in 1977. This new symmetry is broken at the scale FA. We'll see that is of the order of 10 to the 9 to 10 to the 17 GeV for the QCD Axion. This also comes with the Axion, which is a new particle that has been postulated. It cleanses away the CP problem. It's also a cool name for a particle itself. These were actually words of the people who gave the name of the particle itself. All right. Soon we'll also realize that you can have viable models that embed the Axion in larger theories, and they are still used as a benchmark models. And it was also soon realized that the Axion can serve as a cold dark matter candidate, and it's actually nowadays one of the best candidates for the cold dark matter. So I have already talked about this panel. Here is everything you need to know about the Axion, basically. So remember that the coupling with the photon is generated at the loop as a loop diagram, and it's proportional to the Axion mass. The mass of the Axion and the decay constant that we've seen before are inversely proportional. Here I put some experiments that are still looking for Axions. What I want to talk about is the Axion cosmology. So when the Pecei symmetry continuously breaks, the Axions sit at the bottom of this potential in a circle, anywhere between minus pi and pi. This occurs at the energy scale of order 10 to the 9 to 10 to the 17 GeV. But then, when the temperature of the universe falls below order GeV, this Mexican head gets tilted, and the Axion starts to coherently oscillate about the minimum of the true minimum of the theory. This is how the cold dark matter is generated by this coherent oscillation. That this mechanism goes under the name of misalignment mechanism. This is so because the rho of the Axion is proportional to the inverse moving volume, and so behaves as a cold dark matter component. So if you look at from a numerical simulation perspective, you see that if the Pecei symmetry breaks after the inflation, you have a plethora of different patches in our observable Hubble volume, in which the Axion field takes different values between minus pi and pi, and you also observe axionic strings, which are regions in which the Axion field winds up from around some strings that have some energy, and so you have to get these strings to decay away, be washed away somehow, because otherwise it would overcome the energy, the expansion rate of the universe today. So they have to decay, and they also provide as a source of cold dark matter for the Axion. This is the scenario in which the Pecei symmetry breaks after inflation. What happens if it happens to break before? Well, we have, in this case, inflation. So inflation singles out a region of the parameter space in which, within our Hubble patch, we have just one value of the initial misalignment angle that's singled out. So this is the Axion parameter space. I've put the energy scale of inflation on the x-axis. This is directly related to R, tensor to scalar ratio. I have put the axion decay constant here on the y-axis. This is also inversely proportional to the axion mass, which is here. The Fa is bound from below by the astrophysical consideration on the cooling time of objects, and it's bound from above by black hole separating. So the non-observance in LIGO of some effects of axions who have a wavelength comparable to that of black holes. Here we have tensor modes, so non-detection of primordial gravitational waves in BICEP 2 and Planck. And this is the forecast we heard of last Monday for BICEP 2. The axion field itself has been tackled. This is ADMX that has currently looked for these particles in this yellow band here. But there are some forecasts and some new parameters, some new experiments that will further tackle this region of the parameter space in the upcoming years. So this line here, Fa equal h over 2 pi, separates the two scenarios that I talked to you about before. In this region of the parameter space, the axion field generates during inflation. Here instead it generates after inflation. So let's talk about here. In this case, the axion enjoys isocurvature fluctuations, which are constrained by Planck, as we heard a couple of days ago. This is the what we expect, how we can constrain the parameter space for the axion in this case. We can, well, there is a lot of stuff to say and so little time. Here at this region of the point of the parameter space is where the angle becomes of the order pi, and the axion field starts to scan the non-harmonicities in the axion potential. That is when the parameter space, when the axion potential deviates from the pure harmonic one. You can give for a given value of theta, you have a singular value of Fa, so you have a one-to-one relation. Focusing instead of this region of the parameter space, we have the fact that here in this corner you overproduce axions, so this region here is forbidden. This line here corresponding to around 10 to the 11 GeV is what you usually hear for the axion energy scale Fa as the preferred scale for being the axion for the cold dark matter. But as you see, you have a parameter space which is way larger. This value of alpha here is the ratio of axion produced from cosmic strings, from the cosmic string, from with respect to those produced from misalignment mechanism. Numerical simulations tend to favor alpha equal to 10, so you have 10 more times axion produced from string than those produced from the misalignment mechanism. So the axion can sit anywhere and still be the cold dark matter in this region of parameter space. Well, of course, if BICEP 2 measures the tensor to scalar ratio in some portion here, we completely we kill off the idea that the axion can sit anywhere here in this region of parameter space. The situation changes if you assume non-standard cosmologies, that is, instead of having a radiation-dominated cosmology, you can have a moduli-dominated cosmology in which the universe is matter-dominated down to some reheating temperature can be pretty low. In this case, the preferred value of the axion scale is of the order 10 to the 14, 10 to the 15 GeV, where you have this kink where theta is of order 1. So in this model, you can motivate your axion energy scale to be of the order of the GAT scale, roughly, instead of being a new scale of the order 10 to the 11 GeV. My last slide is on ultralight axions and ALPs. So ALPs, in ALPs model, you relax the condition that that you have a mass and F that are proportional to the QCD energy scale squared. You take these two quantities as independent. In particular, ultralight axions have received recently a lot of attention as possible candidates for the cold dark matter, but we see in this panel here, which I took a mass of 10 to the minus 20 electron volt, that the axion in this region of the parameter space, that is when the symmetry associated with the ultralight axion is broken after inflation, in this parameter space here, the axion is subdominant, is a subdominant component, so cannot be the cold dark matter. It can be the cold dark matter here in this region of other region of the parameter space, which could be killed off. So in the next years, a detection of paramolar gravitational wave could kill off ultralight axion as a cold dark matter candidate. And this is my summary.